So exercise number 3. Suppose you're running a randomized experiment and you randomly assign study participants into control and treatment groups. After making the assignments, you study the characteristics of the two groups and find that the treatment group has a lower average age than the control group. How could this arise? So this is an exercise which is dealing with the topic of empirical public finance. And actually, if you think about the situation that we are in since the last year, since last year March, so the COVID situation, it's kind of a highly relevant question. Because by now you should have noted that there are several vaccinations on the market which are used for individuals to get vaccinated, and before they were allowed to be sold on the market, there were several studies conducted, and one importance of those studies is that you need to find out what the effect of the vaccination is, holding fixed everything else. Yeah? So you want to have the direct isolated effect of the vaccination on the health outcomes of individual while holding everything else fixed. So what you typically do is that you take a huge sample of participants and randomly divide them into the control and the treatment group, where the treatment group would get the actual vaccination, whereas the control group would simply get some placebo. And by doing this, like with a high number of people, you make sure that on average the two groups are comparable. So whatever effect or difference that you see in the health outcome of the two groups must be due to the vaccination if you choose a sample of individuals which is high enough. And that's basically the critical issue here, the amount of people who are in the sample. And that's the reason why in this like in exercise 3, we could actually see differences between the characteristics. So yeah, let me just get rid of this. Second. So if you just randomly draw from the population to divide people into a treatment and a control group, this random draw does not guarantee you that the average of all demographic and other variables will be exactly the same for the groups. Okay, so random draws do not guarantee that the average of all demographic and other variables are the same. The average should be the average of all demographic and other variables are the same for both groups. And the reason is, so why? The sample could be small. The sample could be small. But if you increase the sample, more and more, the groups should be the same on average. At some point. Yeah, so an issue, so random draws themselves are not sufficient for guaranteeing that the two groups are the same. But if you draw randomly and you have a very large sample out of like which you're drawing, then those those two aspects together are making sure that the two groups on average should be the same. So this has to do a little bit with the law of large numbers, if you're familiar with this. So let me give you an example. So for instance, an example which has nothing to do with actual humans, but let's consider the toss of a coin. Example, random toss of a coin. So if you draw or you toss the coin 10 times, tossing 10 times, tossing coin 10 times. So if you toss the coin 10 times, you don't necessarily observe the ratio or um, frequency of head and tails, not necessarily the same. Even though you're drawing or you're tossing the coin, of course, randomly, so you're not simply throwing it on the ground such that it's always showing head or tails, but you're really tossing it in a way that it's random. Even though you're doing this when you're tossing it only 10 times, there is no reason why the frequency of head and tails should be the same. But if you toss the coin like 1 billion times, then frequency should be roughly the same. Yeah, this is kind of the idea of the law of large numbers. Good. This brings us to exercise number 4. So, why is a randomized trial the gold standard for solving the identification problem? So this has to do something with exercise number 3, of course. So if you look into kind of the empirical literature in different fields, what you will see is that if for instance in the field of medicine, the gold standard there are double-blind or triple-blinded studies where you have kind of randomized trial in that you want to see or you want to isolate the effect of a medicine. And therefore, what you want to make sure, as I told you before, is that you really make sure that the treatment group, which is getting the medicine, and the control group, which is receiving the placebo, they're the same on average. And this you can only do by making sure that you randomly assign people into the treatment and control group, and you make sure that there cannot be any sort of manipulation by the people themselves who are assigned in the group, but also by the people who are doing the trial, because both of those two behaviors would bias the results. And so um, assigning individuals randomly makes sure that the control and the treatment group are the same on average. Same on average for all characteristics but the treatment. By this, one can, so by this, of course, just keep in mind that I omitted it here, but by assigning individuals randomly and considering a large sample. Yeah, that's also important. Yeah, this was the this was basically the answer to question number 3. So assigning individuals randomly and having and choosing a large sample. So please add this to your notes. So by doing this, one makes sure to identify the effect of the treatment. On the other hand, if you would allow individuals to self-select into groups, this would bias the results since there is a reason why some individuals would self-select into the treatment group and others wouldn't. So we'll start here again. So treatment group and others wouldn't. Okay, so if you would simply, for instance, take the medicine example. So if you would allow for people to self-select into the treatment and into the control group, what would probably happen is that the people who are sick most, so the most sick people, will self-select into the treatment group, whereas people who do not feel sick would simply self-select into the control group. And a consequence, like one problem with this is that there is a reason why some of the people are sick and some of them aren't. So, for instance, the immune system of people who are sick could be weaker than the immune system of people who aren't. And hence, what you would have as a consequence is that the control group would consist of people with a very strong immune system, whereas the treatment group would consist of people with very weak immune system. And as an issue, what would happen is that if you would see an outcome or a difference between the two groups in any health outcome, it might not be fully due to the medicine that you have given to the people who were in the treatment group, but it might have been due to the initial difference in the immune systems of the people which are in the control group and which are in the treatment group. Yeah, so you would bias the results of this study if you would allow for people to self-select into the control and the treatment group. And the only way that you could avoid this is by randomly assigning the persons into the different groups to make sure that they're the same on average. And they do not self-select due to characteristics which could bias the results. Okay, so question number 5. What do we mean when we say that correlation does not imply causality? What are some of the ways in which an empirical analyst attempts to disentangle the two? Okay, so let us be very precise on what we mean when we talk about correlation and causality. So correlation means means that two events tend to occur together. Okay, so that's the first thing. So if two variables are correlated, it simply means that they have a tendency to appearing simultaneously, or yeah, they somehow seem to be related to each other when you're just looking into the data. Causality, on the other hand, means that one event causes the other. So let me give you an example. Or let us first answer the question. So correlation can occur without causation due to a third event. So let me give you a very simple example here. So let's assume that one event is, so the event buying ice cream, and so let's call this event 1, and then event 2 would be visiting swimming pools. So I would argue that whenever a lot of people buy ice cream, a lot of people also visit swimming pools. So correlation between event 1 and event 2. But no causality. So why is there no causality? Well, I mean, because just because people visit swimming pools, it doesn't necessarily mean that this implies that they also buy ice cream. So the event that people like increase their visits to swimming pools does not have a causal effect on people also buying a lot of ice cream. And the other way around, if a lot of people buy ice cream, this is not the causal kind of channel through which implies that people also visit swimming pools, because there is another event, so event 3, which is hot weather, this causes both event 1 and 2. Because if, sorry, let me just correct this there. Because if there is hot weather, then people tend to buy ice cream and people tend to visit swimming pools. Yeah, so the causality here is coming from a third event, which has at first glance nothing to do with the nature of the two events that I described to you before. Yeah, so um, buying ice cream is like the demand for ice cream tends to be very high in situations where also the demand for visiting of swimming pools is very high, but those are correlated and there is no causal relationship, and both are caused by the third event here, which is hot weather, and this basically yeah, has an effect on both the events here. Yeah, so the idea here is to show you that uh, two variables can be correlated, but in practice, like they can be correlated, but in an extreme way, there could be nothing like no relationship between the two variables at all. Yeah, and there might be other factors which are impacting one of the variables to have a tendency to appear in a kind of specific relationship to the other one, which we did not observe. Yeah, so this is the reason why correlation is something different than causality. And how empirical analysts try to disentangle the two is by using a lot of empirical or experimental techniques to basically make sure that we control for everything which could affect the two events that we're interested in order to make sure that we do not miss out something. Yeah, and in practice, it's done. So, for instance, in the health sector, it's done by yeah, by double-blind studies with random assignment. In in empirical work with data, it's done by using techniques from econometrics, as for instance, the instrumental variable approach or the difference in difference approach, which we also got to know in the exercise session for the um, empirical methods of public finance. And yeah, there are many other techniques and tools which were developed in order for making it able for empirical analysts to disentangle the correlation effects from causality effects. Yeah, and there has been a lot of kind of developments in this particular field, which yeah, brought a huge benefit for policy, for instance, because if you think about policymakers who are thinking, for instance, to increase the spending in a particular area of the economy, then you might think of them being like very aware of what consequences the spending would have, and they yet want to get kind of an isolated effect or kind of a they want to know the exact causal effect of their policy change on the economy rather than yeah effects which are due to correlation. Yeah, because it's for them it's important to exactly know what's going to happen if they're going to change the amount of a variable which impacts the economy. And this finishes this question.